Hello, friends. Welcome to the third and the concluding part of our vector series, which is a prerequisite for physics for grade 11. Today's class will be discussing about the vector product. So in the previous two videos, what we have seen is that we have seen how to add and subtract two vectors. We have got familiar with the triangle law of vectors, of parallelogram law of vectors for finding the resultant. Now the question is, what we do for multiplication, because we discussed that vectors can also be multiplied, and what are the techniques that are available for us to take the product of two vectors. First of all, can we think of scenarios where two vectors need to be multiplied? In physics, we have work, which is a scalar. For work done, we need to multiply two vectors. We know that it is force and distance. Torque, which is a scalar, is a product of two vectors. Angular momentum, Lorentz force. So these are all the situations, these are all the physical entities where two vectors need to be multiplied. So if you look at vector multiplication, there are two types that we have. One is called the cross product, which is also called the, one is called the scalar product, which is also called the dot product. And the other one is called the vector product, which is also called the cross product. So when you talk about scalar product, when we multiply two vectors and the resultant, the entity which we get is a scalar, we use the dot product. For example, work is a scalar. So whenever we want to find out work, we use the dot product. So we take both the vectors. In this case, work is a product of F and S, and we apply the dot product for this. The second thing is, when we have two entities, two vectors, and their product is going to be a vector, we use the vector product or cross product. We indicate it with the mathematical operator X. Now, what is the definition of dot product? Dot product is defined as the modulus of this vector F multiplied by the modulus of this vector S into cos of the angle between them. So when you put this symbol, what essentially we are saying is, let us consider the magnitude of that vector, right? Because we know that vector is going to represent both the magnitude and direction. Here we are interested only in the magnitude of the vector. So we take magnitude of F, magnitude of S, and we multiply it with cos of the angle between them. In the case of vector product, we take the magnitude of R into magnitude of F into sine theta, and we also have what is called n cap. N cap is going to denote the direction of this vector, because remember we said that cross product is going to give you an entity which is a vector. So torque is a vector. So when you want to find the direction of the torque, we simply say that the direction of torque is in the direction of this vector n cap. Let's take some examples and try to understand this in a simple way. So if we are supposed to find work done in the below case, we observe that this block is being pulled along the x-axis with a force of 5 Newton, and we are moving it for a distance of 3 meters. Then in this case, we say that the work is nothing but F dot S. So it is 5 Newton multiplied by 3 meters, 5 into 350, into cos of the angle between them is 0. So cos 0 is equal to 1. So we say that the work done is 15 Newton meter. So what about this case? In this case, we see that this is like a trolley which we are pulling in our airport and railway station. So we apply the force in this direction, and that direction is indicated by the angle 60 degrees with respect to horizontal. And under the direction, under the application of this force, if our trolley were to move a distance of 3 meters, then what would be the work? So once again, we use the definition of work, which is nothing but a dot product, and we get the result as W is going to be equal to F dot S, which is nothing but F is for us F cos theta into S. F cos theta is nothing but the horizontal component of this force along the direction of the movement. So basically we would be taking a projection of this force along the axis, which is nothing but this one. So this is going to be F into cos 60. F into cos 60 is going to be 2.5 multiplied by distance is equal to 3. So we get 7.5 Newton. 7.5 Newton is the Newton meter, sorry. 7.5 Newton meter would be the work done in this case. Right. So if you were to ask about the direction of work, we would say that work is a scalar, so it has no direction. Now we come to torque. What is torque? The moment we see this, we understand that we are in a very difficult situation if we are to remove this nut from the bolt. So what we apply using our fingers is nothing but the torque. So we hold the edges of the nut between our fingers and we apply a twisting force. We apply a twisting force in order to remove the nut from the bolt. That is what is called as the torque. So if this is a very tight joint and if we are not able to remove this, then we make use of such implements called spanner, whose job is to increase the distance. So if this is the place where we were applying the twisting force, we now use the spanner and then we apply the force at a far greater distance from the axis of rotation of this nut. So here torque is defined as the a cross product between this distance r and the force F. So torque is equal to R cross F. So what about the direction of this work? The direction of this work in this case, direction of torque basically, direction of torque in this case is going to be along end cap. This end cap is nothing but a perpendicular to the plane that contains both R and F. So we have the plane of the laptop which contains R and F. So this torque that we are going to apply is going to be perpendicular to the direction of the laptop, perpendicular to the laptop. In fact, for doing the cross product, whenever we have two vectors A and B, and we need to find the direction of the product A cross B, we also have what is called the right hand rule. A right hand rule which is used to find the direction of A cross B. We'll be discussing this later when we do lessons in physics. Let's try to understand cross product in a bit more detail. In our case, this is the nut and this is the distance and this is the direction in which we are applying the force. If the force is perpendicular to this distance r, we say torque is equal to r into f into sine of 90. 90 is the angle between the distance and the force. Sine 90 we all know is 1. Therefore, torque is simply going to be the product of r and f. In that case, we call this as r perpendicular. However, if instead of applying the force in a perpendicular direction, we were to apply force at an angle, then what would be the torque in this case? This force which we are applying can be resolved into two perpendicular forces. One is the horizontal force. Horizontal force, we take the projection of F along the x-axis. So imagine if I want to, remove the nut, and if I were to apply a force in this direction, would this force contribute to removing the nut? As you might have guessed, okay, as far as the turning the bolt is concerned, this force has no useful role to play. In fact, if one applies more force, you may actually shear the joint and you may break the bolt, which gets us to the other part of the force, which is nothing but the vertical component. So if you now look at the vertical component here, we see that yes, this is going to be useful as far as trying to remove the bolt is concerned. So this component is nothing but f into sine theta. This is a useful component for tightening or removing the tightening, providing the twisting moment to this bolt. It actually aids in turning moment. So whenever we need a physical entity that requires this kind of a perpendicular component, we use the vector product or the cross product. So torque is nothing but r into f sine theta. F sine theta is nothing but the perpendicular component of the force. So we have the scenario which uses this perpendicular component of the force. So we say this is nothing but F cross S. Let's understand the dot product in a bit more detail. So if I have this block and if we are pulling this in the direction given, which makes an angle of theta with respect to the x-axis, then the objective of the pull force is to move the block in this direction, in the x-axis. So once again, if we were to resolve this force into the vertical and the horizontal directions, and we look at the vertical component of this force F, we see that this F sine theta, that is the vertical component, again has no useful role to play as far as the movement of the box is concerned. So this F sine theta is a useless force. Therefore, on the other hand, if you see F cos theta, that is the horizontal component of this pull, F cos theta, we see that yes, this actually is causing the body to move in the desired direction, desired x direction. Therefore, we say that yes, I want to make use of this force, and whenever we need a physical entity as like this, which requires only the horizontal component, we use what is called the dot product. And that product, which is work in this case, is nothing but F cos theta, the horizontal component of the force, multiplied by the distance S, or we simply say this is F dot S. So this is what is the dot product. Now, we would do some numericals around the dot and cross products in order to get more familiar about this. For example, if we were to have a force expressed as 3i plus 3 root 3j and displacement of 2i plus 2j. And if you want to find the work, how do we go about it? So whenever we mention force in the Cartesian form, we need to give I cap, j cap, because just as we discussed in the previous videos, I cap and j cap are unit vectors which are along the x-axis, and j is the unit vector along the y-axis. This is a Cartesian representation for a force. So if you were to use the definition of work, work is nothing but F dot S. So we say W is equal to vector F dot S, which is nothing but you take this 3i plus 3 root 3j dot 2i plus 2i plus 2j. And we proceed as usual the way we do normal multiplication by using this distributive law 3i dot 2i, 3i dot 2j, 3 root 3j dot 2i, 3 root 3j dot 2j. Now, if we were to look at this, this is 3 into 2, which is nothing but 6, and I dot I. Similarly, this is 3 into 2, 6, multiplied by I dot j. So we need to understand how to apply the dot product between I and I. So for this, we must know that I dot I is nothing but modulus of I. I is a unit vector, therefore that modulus is the magnitude of that is going to be 1. And I once again is 1. Angle between I and I both being along the x-axis, unit vector along x-axis, the angle between them is going to be 0. So I dot I is going to be cos 0 is equal to 1. Similarly, I dot j and k dot k are also, j dot j and k dot k are also going to be 1. On the other hand, I dot j, where I is vector along x-axis and j is a vector along y-axis, are at an angle of 90 degrees with respect to each other. Therefore, I dot j will be 1 into 1 into cos 90. And therefore, j dot k and I dot k also together will be 0. The dot product will be 0. We should use these results in order to simplify this. So what would 6 into I dot I be? 6 into I dot I is nothing but 1. Therefore, this is going to be 6. Similarly, we can use the other results which we got in order to get this as 6. This is going to be 0. This is going to be 0. This is going to be 6 root 3. So 6 plus 6 root 3, not Newton, it is going to be Newton meter or Joule. Then we come to cross product. So in cross product, if we were to find f and if this f were defined as 3i cap plus 3 root 3j cap, and r was defined as 2i cap and 2 plus 2j cap, and we were to find torque, we would say torque is nothing but r cross f, which is nothing but 3i cap plus 3 root 3j cap cross 2i cap plus 2j cap. So like we did in this case, we once again open the bracket and we write the entities. So this would be 3i cross 2i plus 3i cross 2j. Similarly, we expand the other elements of this multiplication. Now, if we were to examine the cross product, we would see that I cross I is going to be equal to 0, because I cross I is nothing but the magnitude of I multiplied by the magnitude of I multiplied by the sine of the angle. Because this is a cross product, we need to take the sine. Sine of the angle between them happens to be 0. And we know that sine 0 is equal to 0. Therefore, whenever we take I cross I or j cross j, k cross k, we get 0. On the other hand, if you were to take the cross product between I and j, I and j are at 90 degrees with respect to each other. Therefore, we get this as I into j is equal to 1. And as per the definition of cross product, the direction of the product is going to be perpendicular to I and j. So if I is along x-axis, j is along y-axis, then k is along the z-axis. Therefore, we say I cross j is equal to k. This can be remembered in a very simple way using this method. We say I cross j is equal to k. J cross k is equal to I, and k cross I will be equal to j. On the other hand, if we were to go in the anti-clockwise direction, then the result is going to be different. For example, if we were to go in the reverse order, if you were to do j cross I, you would not get k, but you would get minus k. Likewise, if you were to do I cross k, you would not get j, but minus j. So you must remember that when you do the cross product, the way we apply the cross product is going to be important. Using these results, we can get 6 into I cross I is going to be 0, and j cross j also is going to be 0. 6 into I cross j, on the other hand, is going to be 1k. So here we get 6 into k, 6k. And this is 6 root 3 into j cross I. J cross I for us is nothing but minus k. Therefore, we get this as minus 6 root 3k. Therefore, the torque is going to be 6 minus 6 root 3 into k. And the units are going to be torque, Newton, meter. So in this way, we have learned how to apply the dot product and cross product when we are given the vectors in the Cartesian form. Hope this was informative. This concludes the three-part series of vectors, which serves as an introduction for doing grade 11 physics. Hope you enjoyed this session. Happy learning. Thank you very much.